All right, so this is a initial rates problem, and I think this is a pretty common type problem for us to run into. And in this problem, what we're going to be asked to do is a number of things, but the most important thing I think would be to figure out what the rate law is. So when we're solving a problem like this, I think it's really important that we're always starting with the general form of the rate law. So the general form of the rate law is going to be the rate equals some constant K, which is the rate constant for this chemical reaction, times the concentration of our reactant, so P4 raised to some power X, and then H2 raised to some power Y. Now, if we're not told any other information about this reaction, these coefficients, they are not going to be related to our orders. As we move forward, we might run into some different situations, but for now, when we're given this sort of type of problem, initial rate data, and we're asked to find the rate law, we do not know what these X and Y values are. And this data is essentially going to be telling us or helping us figure out what those values are. Now, when we're thinking about what this rate law is, basically what it's telling us is it's telling us what the rate of the reaction will be. So this initial rate, this is telling me that this concentration, molarity, is going to be changing at a certain rate. So there's two ways to think about that. We can imagine this P4, we're monitoring the concentration of this P4, and as it goes away, right, this rate is going to be how much is it going away per second. Likewise, we could also monitor the formation of this product. Now, it really doesn't matter which one we're thinking about, because what we're looking at is relative rates. So what we're really concerned about is how these numbers, really regardless of what they are, how these numbers compare to one another. I can see that these two numbers are essentially the same, 3.19 times 10 to the minus fourth, 3.20 times 10 to the minus fourth. That's, I think, pretty safe to say that these two numbers, those two rates are the same. And then here, when I look at experiment 2 and experiment 3, I can see that there is a change, right? This number is actually bigger, 1.28 times 10 to the minus third instead of 10 to the minus fourth. And I know that, the calculation, this is actually going to be 4 times faster. So I can look at that and I can say, relatively what's happening with the rate. And that's really all that's important. It doesn't really matter, are we monitoring the disappearance of this P4? Are we monitoring the appearance of pH3? It's just the relative rate, for each experiment. Okay, enough of that. Let's go ahead and use that information to actually figure out what this X and Y value are. The way to do that is we're going to choose experiments where the only thing that's changing in terms of the concentrations is one thing. So what I mean by that is if I look at experiment 1 and experiment 3, for instance, I can see that in experiment 1, I start with this 0.0110 molar P4, and in experiment 3, I've doubled that concentration. Same thing for H2, going from experiment 1 to experiment 3, I've doubled that concentration. So we do not want to use that set of experiments because we've got two things changing. We want to make sure that we're choosing experiments where only one of the concentrations is changing. We're not really going to be concerned about what's happening with the rate just yet. So we're not looking at changes in the rate. What we're looking at is for my reactants, when I only change one thing in terms of experiment 1 to experiment 2, I'm only changing the concentration of H2. This is staying constant. So I'm only changing the concentration of H2. Now the question is, when I make that change, what happens to the rate? So for instance, if I compare experiments 1 and 2, my concentration of H2 doubles. So we can see that doubling here, the concentration of H2 doubles, and the rate stays the same. So I can look at my rates here, and I can see that those rates are actually staying the same. Now what this is telling me, and really hopefully what this is eventually going to be telling you, is what the order in H2 is, what this Y value is. Now there's a number of different ways for us to think about this or look at this. One way that I like to show would be I'm doubling this, so we can sort of imagine I've got some situation here. I'm doubling my concentration of H2, so I'm going to put a 2 here and raise that to the Y power. Now all of this K and concentration of P4 to the X, whatever this is, it's going to be a constant. It's not going to be changing. So when I'm looking at experiments 1 to experiments 2, and I'm saying it's not going to be changing because this concentration is not changing. So I can say all of that I can just sort of ignore. And what happens to my change in rate? My rate actually stays the same, so I'm going to put a 1 in for that. And now all I'm doing is really solving for this y value. Hopefully you can see, in this case, y should equal 0. And that's really going to be, telling us that changing the concentration of H2 is not going to affect the rate of the reaction. That's what a zero order means. Let's do this next part for P4. So to find the order in P4, I'm going to compare experiments 2 and experiments 3. And again, I'm choosing that because my concentration of P4 is changing, but my concentration of H2 is not changing. So that tells me whatever change I observe in my initial rate, I can sort of correlate that to this change in my concentration of P4. Because my H2 concentration is not changing, the change that I see here is due to the change in this concentration of P4. So let's do that. Experiments 2 and experiments 3. And really, you can almost think about this as going, you're comparing experiments 2 to experiments 3 because the concentration is doubling here. Then we're going to see what happens over here as well. So my concentration of P4 doubles. And like I said earlier, the rate is going to quadruple. Rate times 4, quadruple. So if you take 1.28, so the way that I know this, right, so let's sort of do a little aside up here. If you take 1.28 times 10 to the minus third and you divide that by 3.20 times 10 to the minus fourth, you get a value of 4. That's how I know that the rate has quadrupled, it's increased by a factor of 4. That's how I'm calculating that. So when we're doing these calculations, you might get confused about which one to put on top, which one to put on bottom. I think in general, it makes the most sense to just put the bigger number on top. So I've got a bigger number here, I'm going to put that on top. I've got a bigger number here, I'm going to put that on top. When I compare, what's happening here, it's easy for us to see that this just doubles. But if you took 0.0220 divided by 0.0110, you get a factor of 2, right? So this, again, is telling us what the order is. The way that it's doing that, I could do the same sort of scenario here where I'll say my P4 concentration is doubling. And now my rate is increasing by a factor of 4. So I get this factor of 4 here. That's what's happening to my rate. And I can solve for x, and hopefully we can see that x should equal 2 in this case. And the significance of that is just that really what it's telling us is that if you increase the concentration of P4, it's really going to increase the rate. It's going to be an exponential growth because we're going to square that increased concentration. We're going to see an increase in our rate by a factor of 4. So these x and y values, that's really telling us, we can fit those into our rate. So if I wanted to find the rate law, I would say that my rate is going to be equal to k, which we have not solved for yet, but we will, P4 squared, and then H2 to the 0 power. Now, H2 to the 0 power, that goes to 1. So we can actually ignore that. We don't need to include that if we don't want to. But we can, it doesn't really matter. But we don't have to. So we could simplify this to rate equals K, concentration of P4 squared. Now, the next step is solving for the rate constant. So this is all A, right? This is A. So for part B, it asks us to find the value of the rate constant. Now to find the value of the rate constant, we're going to use our data. So we're going to say, well, I can choose any experiment, and I'm just going to plug in my concentration for P4. I'm going to plug in my initial rate for my initial rate. You could plug in your concentration of H2 here as well, but we know that that's just going to go to 0 or go to 1, so it doesn't really matter. But you can just plug in your data, and again, you could choose any experiment, plug in your data, and see what that K value is. So sort of solve for K. So for this experiment, I just chose this experiment 1 data. So I plugged in 3.19 times 10 to the minus 4 here, plugged in 0.0110 here for P4, and then I solved for K. So in this case, so we'll put a little b here. K should equal 2.64. So that's the value of the rate constant. We could think about the units of the rate constant as well. So if I have this rate here, the rate is always going to be in molarity per second. And basically I just need to figure out what units I need to have for K to cancel out or to make it sort of work that I get the proper rate units. So I can see in this case my units here should be 1 over molarity times seconds. If those are my units for this K value, then when I multiply that by molarity squared, this would be molarity squared. Molarities are going to cancel out. I'm going to get molarity over seconds for my rate. So that's the proper way to do the units. Now, For the last part, the initial rate of the reaction when P4 equals 0.242 and H2 equals this 0.0133 molar. Again, all I'm going to do is plug that data in. So now I've got my rate law, I've got my rate constant. So all I need to do to figure out the initial rate of this new reaction is just plug that data in again to my rate law. So I've got a K value here, I've got an initial concentration of P4 here, I'm going to plug that in right here, and I'm going to solve for the rate. So that's what we're looking for here. And again, this H2 concentration, because it's zero order, really doesn't matter. So when you do that, for C, you should get a value for your rate equals 0.155 molarity over second. So that should be your rate for that reaction. All right, so hopefully that helps. Let me know if you have any questions. Thanks very much.